Hey, General Chemistry. We are starting a new chapter on the behavior of gases. So this is going to be Chapter 14, a new set of notes in your notebook. So let's get started. First, we're going to talk about what's called the kinetic molecular theory. Now that sounds like a mouthful. All it means, or all the theory is about, is it's used to describe the behavior of atoms in a gas. Okay, and it's based on the idea that particles are always in motion. And that's probably not a new idea for you. We say if they're a solid, they're tightly packed together, they're vibrating slightly, okay, so that they're still slightly moving. And in a liquid, they can move up and around each other. They can't fly off anywhere, but they have more mobility. And in a gas, they can move anywhere they want. So in this particular chapter, we're just talking about the properties of gases, okay? So when we're talking about these properties of gases, and there'll be a number of gas laws we're going to learn about to describe how they react, we are using an ideal gas. And the kinetic molecular theory is based on an ideal gas, meaning that it perfectly fits all the assumptions, which some gases fit these assumptions really well, some don't. There's always exceptions, but in a real world, there's so many other variables going on, other things affecting it. So we're just going to say we're talking about ideal gases that do exactly what we want them to do. So let's talk about the assumptions of this ideal gas law. So in an ideal gas, we assume that all gases are spaced far apart. Okay, so just like we said, solids are tightly packed together. Okay, and liquids can move up and around each other, and then our gases can move all over. So if we think of a solid, and you might want to sketch this in your notes too, these usually, depending on the solid, they're pretty uniformly packed. So if these little dots are my atoms, they're uniformly packed into a tight space and they're slightly vibrating. A liquid would be not as tightly packed. They can move up and around each other, but they're still not everywhere. They're pretty much still held together. Okay, but they can move up and around, they can flow, right? Like we can pour water, but you can't pour a solid, they all come together. And then for a gas, they're even further apart, okay? And they can basically go wherever they want. They're not really tied together. They're not really held together. Okay, so if you can think of just the atoms of these things, solid, liquid, and gas, that'll be helpful as we go through some of these assumptions. Last part, collisions between all particles with other things are elastic. If you might remember that word from your freshman year, we talk about an elastic collision. It's a physics term. It just means that just like a rubber band is elastic, I can stretch this rubber band out nice and far, but it always goes back to the same shape. Okay, so that's the idea that no energy is lost. So if my gas bounces into something, it's going to retain all its energy. So just like these retain their shape, the elastic collision means that the energy is consistent or conserved. Again, another way of saying that is no kinetic energy, that's what Ke stands for, kinetic energy, is lost. And remember, kinetic energy is the energy of motion. Okay, so even though it's bouncing off something, it's not losing any of its energy. And the last one, gas particles are always in motion. Okay, we already kind of said that. They're always in motion, they're always moving, and they're moving further apart usually. Moving on to some of the key terms to describe the nature of gases. The first one we're going to talk about is expansion. Okay, now gases can expand, and our definition here says gases have no definite shape or volume. When placed in a container, the gas will fill the space. So to talk about this, I have two different shape size balloons. We have a big one and a littler one. So all right, so my first balloon, right, obviously I've put in some air using my lungs. Okay, nice big one. And my second one, all right. So if we take a look and we talk about expansion, obviously these are two different shaped balloons. Okay, and the reason we can get two different shaped balloons is because gases have no definite shape or volume. That means they take the shape of their container. I probably should have made these a little bit less tight. But this, I can change the shape, right? I can compress it, All right, depending on what I want it to do, it's going to take the shape of the container. If I filled my water bottle with air, it would take the shape of my container and it would fill its container. That's the difference between liquids and solids. Solids, if I dropped some solid rocks in here or something, it would just sit at the bottom. It wouldn't take the shape of the container, right? It would just stay in its own shape inside the container. Liquid, I don't know if you can see that, I have some water in here, takes the shape of my container as much as it can because it has a definite volume. It won't fill the container, right? It has takes the shape, but it won't fill the container. So we say liquids have a definite volume, an indefinite shape, and then gases have an indefinite volume and shape. No definite volume, no definite shape. So if I pump this full of gas, it would spread out to fill the whole container, right? And it takes the shape of the container. Just like these balloons are two different shapes, and they're going to fill the space that they're given, okay? And because they're always in random motion, they're always moving apart. So right now, inside of my balloon, I have all those particles of air moving around, hitting the sides of my balloon, and it's that motion that keeps it blown up. The reason why, even though they're not being forced to go, they are still pushing outward on the outside of the balloon. That's why it's nice and taut, okay? A few more things. Fluidity. Just like a liquid flows, like we can pour this water out, gases can do the same thing. Gases can flow up and around each other. And we might look at a cool demonstration to talk about this, but because those particles can move up and around, they can flow just like a fluid. Low density. So even though this balloon looks pretty big, it has a very low density. Remember, density is grams per milliliter. Okay, so it's not going to have much mass, right? It can flow up in the air. It doesn't have much mass, but they're because those particles are so spread apart. If we filled this with water, it would be heavier, right? And if we filled it with a solid, it'd be even heavier, and it would be much more dense. So it's how many particles are in a given space. Okay, think of a dense forest. There's a lot of trees in that amount of space. So there's a very low density, 1/100th the density of a liquid. Compressibility, we've kind of mentioned that, it's easily compressed. So I can easily compress this balloon into the shape that I want it. And if I compress it too much, the pressure will build up and it'll pop, right? But that's a unique property of gas. So if you think of a solid, okay, so what do I got here on my desk? Oh, rubber band ball, perfect. So this rubber band ball, I can't compress it like I can this nice easy balloon, right? I can compress that to the size I want it to be. Okay, and I did fill it with a lot of air, so it's not the easiestly compressed, but if I had, if this rubber band ball was made up of air, I could easily compress it, okay? Same thing with a liquid. You can compress a liquid to a certain amount, but it's not as easily compressed as our gases are going to be. And then diffusion. And this is just a property that we see often, and it happens a lot easily with a gas. A lot of times we see this with other things as well. Just means the spontaneous mixing of particles of two substances, so you can read that, because of their random continuous motion. Okay, so if this balloon was filled with perfume, okay, I could pop it, and someone sitting in the back of the room, it would smell really strongly here to me. Eventually it's going to diffuse out, and then it would take a little bit to get to someone in the back of the room to smell it. Just like when you light a candle, it takes a little while to fill the space, and you can smell it all over. And again, diffusion's happening because those particles are bumping into each other. So if I have a lot of perfume here, it's going to bump into each other and eventually spread out to the rest of the room. And let's talk about pressure. Okay. Pressure is an important idea when you're talking about gases, because a lot of times we're talking about how pressure affects the volume, affects the temperature. So let's define it. Pressure is defined as the force per unit area on a surface. Okay. Gas pressure results from the spontaneous collisions of billions of gas particles on an object. So right now, this balloon has pressure, and I know because it's full, right? Otherwise it would just be an empty balloon. So it has pressure. All those gas particles inside are moving around, bouncing off each other, and bouncing off the side of the plastic balloon. Okay? So if I wanted to, here's just a little equation, pressure. To figure out the pressure, we take the force divided by the area, and that would be the area of the balloon, how much space is in here. Okay, so if we want to increase the pressure of this balloon, I could add some force. Okay, so if I add force on either side, and I close it, now I have a lot more pressure inside that balloon. And if I push hard enough, I could probably pop it. I don't want to pop it. It makes me nervous. Okay, so I can pop it if I add enough pressure, right? And as I add pressure, what happens to the area? It gets smaller. Okay, right? The space around there gets smaller. So that's pressure, and we'll be talking more and more about pressure. One of the phenomena that's going on that we should have talked about in our demonstrations today was atmospheric pressure. So there's gas all around us. The difference between living on Earth and being in space is that everywhere we go there's gas held in by our atmosphere. So there's a certain amount of pressure pushing down on us at all times because of the gas that fills our atmosphere and fills our environment. This exerts a certain amount of pressure on us. And think about this balloon. There's pressure pushing all over on this balloon, okay, keeping it the shape it is. Now, when I had a deflated balloon, you'd probably see that's a lot smaller, okay? And when I put air in, it got a lot bigger. Now, if we lowered the pressure, if there was no atmospheric pressure, I could probably get this balloon a lot bigger. It says this pressure decreases as you go higher in the elevation where there's less air. So if you ever climb a mountain, okay, or you go to a mountainous region like Colorado, they have a lower atmospheric pressure, okay, because there's less air, there's less things pushing on it. Okay, and if you think about up in the atmosphere, less pressure, and move it down. How do we measure atmospheric pressure? We use this equation, pascals as a unit of pressure. N stands for newtons, which is the unit of force. M is meters, a length, okay? And this is a very small unit. It's a very small unit of pressure. We can also use millimeters of mercury, and that's a barometer. That's I have a picture coming up. Or we can use atmospheres, which is another unit of pressure, saying one atmosphere, how much atmosphere is pushing down on us. We compare that value to an atmosphere. And 1 atmosphere is 760 millimeters of mercury. So let me explain that. STP means standard temperature and pressure, which we'll talk about later. If we take a look at this picture I have, let me move this over. This is what a barometer looks like. All right, it's different than a thermometer because it's not testing temperature, it's testing pressure. So we have a tube. Inside is a vacuum, and that just means there's no gas in it. And this is mercury at the bottom. The air pushes down on that mercury, and when the pressure increases there, it forces the mercury up the tube. And depending on how far it pushes it up, that's how much pressure. So the higher the mercury, the higher the pressure, because that's the air pushing down on it. All right, I think that's going to end our notes for today. So we've talked about some of those properties of gases. Hopefully you got some of that from our class today. And we've talked about pressure and how we measure it. We measure it using a barometer and these units of measurement. All right, I hope this makes sense, and thank you for your time.